During this session on design for reliability, I will be continuing my discussions on the other important issues related to general reliability function. Is it okay? So, any exercise on reliability, it all depends on that how accurately, how meticulously, you can explain the reliability function, how you can model the reliability function. So, in this context, we need to discuss the general reliability function from several perspectives. Now, in this particular lecture session, during these lecture sessions, I will be discussing cumulative and average failure rate, the so-called bathtub hazard rate curve or the life cycle curve, probability distributions to model failure rate, and exponential reliability function. Specifically, I will be discussing details about the exponential reliability function. There could be many other types of reliability functions, but exponential reliability function is very common, and many a time we refer to this one for modeling reliability. That is why we will be discussing exponential reliability function in detail. Now, we know that for modeling reliability, given a particular product or given a particular component or a systems, first thing you must know or you must be referring to the time to failure, and you must be able to explain it properly. So, obviously, assuming that the time to failure is a random variable. So, obviously, I must know what could be its possible distribution, right. Now, so once you have collected you collect data on the time to failure, okay, and then you refer to its distribution, like say probability density function, then cumulative distribution functions, and then you go for reliability function. And now we have already mentioned about the instantaneous failure rate, and when you have the expressions for the instantaneous failure rate in the last the lecture sessions have referred to the instantaneous failure rate. That means at time t equals to t. Obviously, from this instantaneous failure rate you can compute the cumulative failure rate and as well as the average failure rate. Is it okay? So how do you get the expressions for the cumulative failure rate, which is referred to as the CFR, okay, over a period of time t. That is why it is known as the cumulative failure rate. So, this is given as these notations we have used, that is LT is equals to 0 to t lambda t dt. Is it okay? So, now you have this expression for CFR. Now, the next expression is AFR, that means the average failure rate. That means the defined between two times. Is it okay? That means at time t1 and at time t2. Is it okay? So, failure rate I compute at time t1 and failure rate also I compute at time t2, and then I compute the average. Is it okay? So, how do you compute? That means this is the expression 1 upon t2 minus t1. Is it okay? Integration t1 to t2 lambda t dash into dt. So, ultimately you have these expressions. So, that means the natural logarithm RT1 minus natural logarithm RT2 divided by T2 minus T1. So, the steps you follow, and you know that I presume that there will be no problem for you to getting these expressions. Is it okay? So, ultimately average failure rate between the time T1 and T2 is given by this expression. That means the natural logarithm of RT1 minus natural logarithm of RT2 divided by T2 minus T1. Is it okay? So, it is a rate That's why there is a time dimension. Okay. Now, equation of average failure rate can be simplified by noting T1 equals to 0 and T2 equals to T. That means what we are saying that at this point in time, at time T equals to 0, when the product starts functioning, what could be the failure rate? Is it okay? And when it lasts, say for say T time period, capital T time period, it has survived capital T time period. So at that point in time, that means T equals to capital T, what is the failure rate? Is it okay? So this is a particular case, and you will apply this rule. So ultimately what you will find, if you get these values, then and this is ln r0 minus ln rt. Is it okay? So this is t minus 0. So this could be capital T, this could be capital T. Is it okay? So ln divided by lt divided by t. So that is a particular case. Is it okay? So you compute when the general expression of AFR is known. So you get the particular values of t, and then you get for the corresponding the time period, what is the average failure rate. So if AFR t is a non-decreasing function, that means the failure rate is increasing. Is it okay? The failure distribution is characterized as having an increasing failure rate average. So we call it IFRA. Now, is it a desirable situation? It means these conditions you have to check, you have to control. Is it okay? Now, how to do that? What are the technical means with which you can control this increasing failure rate? Okay, average. So there are many ways you can arrest, you can control this, the increasing failure rate average. It's okay. There could be engineering solutions, there could be, the technical solutions. If the function is non-increasing, that means decreasing, what could be the possible reasons that you have to find out? Is it okay? Later on, when you refer to the exercises, you will find that you will be asked to identify the possible causes of getting this sort of say the behavior of the process or of the product. That means increasing failure rate average. Is it okay? So what could be the possible reasons? And if you have this sort of the behavior, so what are the possible means with which you can control this? Is it okay? And similarly, if the function is non-increasing, then this is a desirable one. So that means it may be, you can relate it to say the design of the product, you may relate it to the functioning of the product. Is the functioning of the product. The distribution has a decreasing failure rate average. Is it okay? So there could be many types of exercises we can assign related to these two kinds of situations. Okay. Now I will be discussing an important say curve that is always we refer to any discussions on reliability whenever we try to say the model reliability. We always refer to the life cycle curve, and technically this is referred to as a hazard rate curve, but it is also referred to as the life cycle curve. And as this the life cycle curve or the hazard rate curve, okay, it looks like it resembles a sectional view of a bathtub. So many a time this is also referred to as the bathtub hazard rate curve or simply bathtub curve. Is it okay? So in any exercise on reliability, we check whether the concepts or the bathtub hazard rate curve is applicable or not. So let us discuss this bathtub hazard rate curve in detail. Now this hazard rate curve is a typical bathtub curve. Okay, I have already mentioned, especially when representing the failure rate of electronic components. I am not saying that this the life cycle curve, the bathtub curve is this concept is applicable for all types of products, but the majority of the products you may assume that this particular curve is acceptable or is valid. So, mostly electronic components. Mechanical components may not necessarily follow this type of failure pattern. Is it okay? So, you have to look into the design, you have to look into the characteristics of a particular product before you conclude whether the bathtub curve is applicable or not, or the life cycle curve. But what the researchers, what the practitioners have observed over the years, for the majority of the components, for the majority of the products, okay, this concept of bathtub curve, the life cycle curve, is applicable. Now, let me explain this life cycle curve or the bathtub hazard rate curve. Now, this is basically a plot of, say, failure rate versus time in respect of a particular product. So, y axis represents the hazard rate or the failure rate, and x axis represents over the time. Now, here when you start using the product, is it okay? Now, over during the entire life of the product, that means the product is born here, you start using it, and the product dies at this point in time. So, what we say that whatever may be the quality of the product, whatever may be the design level of the product is born and product also dies. So, during this entire life period, is it okay? Now, the failure rate actually varies, is it okay? So, at the initial stage, you will find that the failure rate is very high, and then over the time period it starts decreasing. That means, during this phase, obviously when you find that the hazard rate or the failure rate is very high, you have to take some corrective measures. Is it okay? So, initially you never know, you have designed the product, you have started using it after its manufacture, and then in the real the situations or real conditions, you start working. So, obviously when it starts working in a real environment, okay, the performance of the product may not be that predictable. So, usually what happens, initially as product is a new one, that means the failure rate, hazard rate is very high, but ultimately over a short period of time it reaches a particular level, that is the failure rate. Is it okay? It reaches over here. So, what is this phase called? So, this phase is called the burn-in period, okay, or the debugging phase, right? And then so there could be some failures over here. Now, what you try to do, that means you take some the corrective measures over there, so that the failure rate reaches over there, and then the useful life period starts. That means, what you try to do, suppose a car you purchased, you started using it. So, initially you never know that whether the car will perform as per its intended function at the initial stage. So, there could be many failures. So, what you try to do, you just be in touch with the servicing, and they will do the servicing, and once the service is done, then you will find that you start using the car for the next 5 years or next 6 years without any problem. So, what we say that now once this burn-in period is over, now you have entered the useful life period, and this will continue, and during this useful life period, what you have noticed, that the failure rate is almost constant. It should be at the minimum level, and the failure rate also should be minimum. Then what happens, that obviously at a certain point in time, that means suppose between time t1 and t2 time periods, maybe 5 years, maybe 6 years, what you will find, now the aging process has started in. So, as the aging process starts, what happened, that obviously the failure rate or the hazard rate starts increasing, and ultimately at some point in time what you have to do, that means the hazard rate has reached that level that you have no other alternative but to withdraw the product or that particular unit. That means it has lived its full life. So this period is known as the wear out phase. So whenever you refer to the life cycle curve or the bathtub hazard rate curves, that means this looks like a the bathtub. Is it okay? That's why it is referred to as the bathtub curve. So you have three phases: burn-in period, a debugging phase. Is it okay? Child mortality phase. Then you have the useful life period phase, and then you have the wear out phase. So these three phases are noticeable in any say life cycle curve for a product. Okay. So this for the given product, you must have the corresponding data with you. Is it okay? Now, decreasing hazard rates is also called the burn-in period. That is, you refer to the phase 1. Is it okay? Burn-in period. Other names for this period are the debugging period, the debugging phase I have already mentioned, infant mortality period or child mortality phase, and the break-in period. This is also referred to as the break-in period. Different names are given. Failures during this period are normally attributed to design. Is it okay? Because whether your design is really is good or bad, you will come to know when you start using the product. Is it okay? So the failure may be due to the design or the manufacturing defects, welding flaws, cracks. There could be several reasons. So I have just highlighted few reasons: defective parts, poor quality control, and contamination. Now here one particular point you should focus on, that is poor quality control. This also could be the main reasons of early failures. Okay. Now next is when you reach the useful life phase, that means constant part of the bathtub hazard rate is known as the useful period. That means it is essentially the constant failure or failure rate. That means that your almost your performance on the product is predictable, which starts after the infant mortality period. That means during the infant mortality period, you need to take some corrective or the preventive measures related to design, related to manufacturing, and accordingly so you improve the quality of the product, and ends just before the wear out period. Is it okay? That means when you declare the product to be an aged one and quite old, and you assume that the aging process has started. Is it okay? So the environment, random loads, human error, etc. cause this. Is it okay? So you might say that why not the failure rate comes down to 0. So obviously there will be some uncontrollable noise factors. Is it okay? Like say the environmental conditions, right? Like say the randomness in loading. There could be human error. Is it okay? So human error, unintentional human error, it's absolutely it's a random occurrence. So there could be such causes. Okay, these the system in the system these causes do exist. So because of this there will be a failure rate or say hazard rate, but it should come down as minimum as possible. That is to be ensured. Now next comes the wear out period. Now this period starts when a component has aged or bypassed its useful operating life. Is it okay? The number of failures during this time begins to increase. That's why the failure rate has increased. Failures that occur during this useful life are called random failures, since they occur randomly. Is it okay? So you need to when you collect the data, and particularly these exercises is very useful in the context of quality, in the context of reliability study. That is whether you can conclude that whether the failures are occurring due to some random causes. Okay, so this exercise is very important. We refer to many case studies on quality and reliability, and so when you start analyzing this data. So you must be, as an expert, as a learner, you must be able to identify the random causes also. Okay. So this is caused by fatigue, corrosion, aging, friction, cyclic loadings, etc. Whether it's a mechanical systems or electrical systems, these are the the general reasons. Okay, you come across. Now, how to represent this the failure rate curves for all these three phases? So hazard rate can be represented at, this is 1 lambda Ct minus 1 plus this is the expressions we have. Is it okay? T to the power b minus 1 beta e to the power beta t to the power b. Is it okay? So you have three parameters, alpha, say the beta and gamma. Is it okay? So this is the expressions lambda t, and these are the b, c, beta and lambda. These are all greater than 0. K lies between 0 and 1, and t is greater than 0, c equals to 0.5 and b equals to 1. So where b and c the shape parameters, beta and lambda is a scale parameters, the k, and t equals to the time. Is it okay? So these are this we will be again referring to. So how to model all these three phases. Now let us talk about this is the modeling the failure rate. And while you try to model the failure rate, you refer to the corresponding probability distributions. Now there are two types of situations you come across as far as modeling reliability is concerned. First one is there could be cases where you assume that the failure rate is constant. So the constant failure rate models we will be referring to, that is the first part, and on the second part we will be referring to the time dependent failure models. Is it okay? So there are so all these models are classified under two categories, right? Now let us talk about, I will be just now I will be talking about the constant failure rate models. That means what we will assume that the product or the system or the component or the process, so they are at the the useful life phase. It's clear? That means the debugging phase is over. It has not yet reached the the burn-in, say it has not reached the declining phase or the wear out phase, but it is in the constant failure rate case or the phase or the useful life phase. Many systems exhibit constant failure rates, and the occurrence of failures is purely random. This point I have already mentioned. There are several probability distributions available to describe the failure process. Is it okay? So the choice is yours. That means you have to collect data, you have to analyze the data, and then you check, and you must know what is the physical systems. Is it okay in getting the data, and there must be some physical basis of assuming certain distributions, or whether the distribution is in empirical form. So that these distributions can be either in the empirical form or in the standard form. Is it okay? So so that exercise you have to do. So what we are saying that when you refer to different kinds of data sets, you may come across the different kinds of probability distributions to describe the failure process. Among them, the exponential probability distribution is the most widely used distributions in reliability analysis. Is it okay? So it's a single parameter the distribution you are all aware of, and exponential probability distribution is a particular case of Weibull distribution. Is it okay? So I repeat that it's a special case. That means exponential distribution is a particular, it's basically a part of the Weibull distribution. That means a special case of Weibull distribution is exponential probability distribution. Okay. Now let us talk about the exponential reliability function. That means whenever you try to model the useful life phase of a given product, assuming that the bathtub curve concept is valid. Now, we need to model it. So, we start from this, that means lambda t is equals to lambda. It is not is a function of time. So, it is a constant we are assuming. So, what is probability density function, that is f t is equal to lambda e to the power, that means e to the power minus 0 to t lambda d xi. So, that means this is lambda e to the power lambda t. So, this is dt actually, lambda dt, is it okay, equals to lambda e to the power minus lambda t, is it okay. So, this is a typical, this is the density functions, the probability density functions of t greater than 0 is for the exponential distribution. So, what is RT? RT obviously you will get, that is dt lambda into dt is equals to e to the power minus lambda t. So, whenever you assume that that exponential say failure rate, so you say that RT, that means that the component or the product will last for t time period, is it okay, that is a reliability function, is e to the power minus lambda t. So, obviously say this is qt's distribution function, that is 1 minus e to the power minus lambda t. Okay. Now, expressions for qt and rt can be derived using the failure rate as follows. So, qt is 0 to t lambda e to the power minus lambda t into dt is equals to, ultimately now you go for these expressions 1 minus e to the power minus lambda t. So, this part already we have derived, and so the sum of the equations is always equal to unity. So, you get RT is equals to t to infinity, that means lambda e to the power minus lambda t due to the power minus lambda t. So, these two expressions you must remember, and then this is the graphical representation, that means lambda versus t. So, you will find this is constant, and then this is basically lambda t versus t. Okay. So, this is a function of t, this is the second case, is it okay. As the time passes, what you will find that the lambda changes, so that is the second case, is it okay. That means hazard functions and failure density function. Okay. Then you have these reliability functions we have, is it okay. So, as the time passes, that means this is RT versus t. So, it is quite obvious that if t increases, the RT decreases, is it okay. And this is the cumulative distribution functions basically, right. So, as the time passes, the value of qt increases, and the limiting value is 1. Okay. So, this is just a graphical representation. So, the parameter is called the failure rate, and it is equal to the number of failures per unit of time, is it okay. That is the failure rate. Again we are referring to, we need to define the failure rate in explicit manner. So, we can derive the expressions for reliability and unreliability as follows. Probability that no failure in the time interval 0 to t. So, that is basically RT is equal to e to the power minus lambda t, and failure in the time interval 0 to t, that is qt 1 minus e to the power minus lambda t, is it okay. So, for the exponential reliability function, let us consider an interval of time t and t plus small t. So, let event A equals to failure during time t, event B survival up to time t, no fail, that is no failure in time interval 0 to t. That means between 0 to t no failure, and between t and t there will be capital T and t, there will be a failure. So, then A ending B is equal to survival up to t and failure during t and t plus t, is it okay. So, you have these expressions ultimately. So, e to the power minus lambda t minus e to the power minus lambda t plus t, is it okay. So, ultimately this is the probability that there will be B is the survival up to time t, that is e to the power minus t, is it okay. So, another way we are getting the expressions for the reliability. So, exponential failure density functions, so f t versus t, that is this one, Is it okay? So how do you define this density function, that is lambda e to the power minus lambda t, t is greater than 0. Okay, so with this the basic say the introduction to the failure rate function. So what we are trying to focus on, that is how to model the reliability. So the reliability function must be explicitly specified for a given product, and for that data are to be collected, and three things you have to do. Like, so the first, you must be able to specify the probability density function. Then the probability density function, then you define the cumulative distribution function, and then the cumulative distribution functions, now you refer to the reliability function, and then you check for the different time periods. Is it okay? What is the reliability value of the reliability? So what we will observe that as the time increases, the value of the reliability decreases. Is it okay? So that is the general conditions in almost all cases we will observe. Now what you need to do, you need to specify the time period. That means the survival time. Many a time when you refer to the warranty of the product, that means you say for a given product, say like an industrial product, say a transformer, we say that you start using it, you find that I am guaranteeing you within the 10 years time period, I am giving you the warranty of 10 years. It means that already I have tested its reliability, and I conclude that within a 10 years time period, even if it is a continuous running, okay, there is hardly any chance of its failure. Is it okay? That means you have to specify certain time period where you are very much sure that there will be hardly any probability of failure. So at least whenever we try to the study reliability of a product, ultimately whatever the results you get, it must be reflected in assigning a particular the dimension of the quality, that is basically the warranty. Is it okay? So it's a very important dimensions of quality. You get an idea that how whether the product quality is excellent if you look at its warranty period, warranty. So it is essentially, with respect to the reliability data, we are concluding about the many dimensions of quality.